Okay, in this video I'm going to talk about the Napoleon's theorem. This is closely related to the previous two videos about the first Fermat-Torricelli point and the second Fermat-Torricelli point. So basically we have the same setting. Let's say that we have an arbitrary triangle, and we consider the equilateral triangles constructed on the sides of this triangle. So either to the inside or to the outside. So like both of them are called the Napoleon's theorem, but these are actually two different statements. And they correspond to the first Fermat-Torricelli point and the second Fermat-Torricelli point. So for the first Fermat-Torricelli point, we considered the equilateral triangles to the outside. So like this. And here is like this. Yeah, like there is no place for this point, but like anyway. So this is kind of the same setting as for the first Fermat-Torricelli point, and now the main statement is that the centers of this triangles. So these are three equilateral triangles. But the initial triangle was arbitrary. It can be any triangle. So the centers of these triangles, they themselves form an equilateral triangle. So this triangle is equilateral. So let's write this. So if the original triangle is ABC, then we denote these points as P, Q, and R. R is this point. So let's just remove the name. Yeah. So we'll write here. Napoleon's theorem, and the point is here. And the theorem now says that the Napoleon's theorem. So it says that like I didn't denote this. So let's denote the centers by let's say X, Y, and Z. So the theorem says that X, Y, Z, this triangle, is equilateral. Another theorem is that, let's call it theorem 1. And another theorem is that, like if we have let's draw the picture here. So if we have we construct the triangles to the inside, so like this, and like this. So if we basically the same construction, except we take we construct the triangles to the inside instead of to the outside. And again, we take the centers of these triangles. So if the original triangle is ABC, the centers would be so the center X Y, and this center is Z. So then these 3 points are also form an equilateral triangle. So theorem 2. Well, let's denote them X prime, Y prime, and Z prime. So theorem 2 says that X prime, Y prime, and Z prime is also, the triangle is also equilateral. Yeah, so the proof would be similar. So like I will show like more in detail theorem 1 and theorem 2 would be similar. The idea is the same. So let's so basically we will use the results that we already proved for the first when we considered the first Fermat-Torricelli point. So there what we proved is that the lines connecting, so the lines AP, BQ and CR intersect at a single point. Which is called the first Fermat-Torricelli point. So let's draw this. So like it doesn't necessarily pass through X. So like I want to deliberately to draw it that doesn't pass. So these 3 lines. So they intersect at a single point, and this so denoted by, well, we could denote it T1, but like let's denote it T, so this is the first Torricelli point, but we also proved more. We proved also that the angles between these lines are all 60 degrees. So all of these angles are 60 degrees. And like the same as the angles in the equilateral triangles, right? And well, it's immediately follows from this, but like we also proved, like we proved it before that the quadrilaterals like consisting of these equilateral triangles plus this intersection point T, they are all cyclic. So the quadrilateral QCT. So let's list all of them. AQCT, CPBT, and BRAT. All of these 3 quadrilaterals are cyclic. So we proved it in in the previous, like in one of the previous videos about the first Fermat-Torricelli point, and like if you know that this angle is 60 degrees and this angle is 60 degrees, it immediately follows that this quadrilateral is cyclic, like it's one of the criteria. So yeah, so now we see that. So let's draw actually these circles. So there are these 3 circles that all intersect at point T, right? So this quadrilateral cyclic, it means, like, by definition, that there is a circle that passes through all 4 vertices of this quadrilateral. So these are the circles, and in particular we see that these circles are the circumcircles of the equilateral triangles, right? So x, y, and z are the centers of these circles. So x, y, and z, x, y, and z, so they're the centers of the triangles, of the equilateral triangles, but since it's the circumcircles of this equilateral triangles, so they also correspond with the center of the circle. So are the centers of the circles. Okay, and now we see that, so since these are the centers, so the lines, so let's consider xy. So let's say, so xy is the line connecting the centers of these 2 circles, right? But so TC is the line that contains the common chord of these 2 circles. And like it is a well-known property that they are perpendicular to each other. So the line connect, so like let's draw it separately. So if we have 2 circles, then the line containing the common chord, this line is perpendicular to the center, to the line connecting the centers of the circle. It's perpendicular. So this is a well-known property, and now so the same as for the, so we established that, let's write it here, so that xy is perpendicular to CT, and but similarly, like we have for the other points as well. So so yz is perpendicular to AT, and zx is perpendicular to BT. So yz is perpendicular to AT, and zx is perpendicular to BT. So now what are, like, since we know the angles between the lines AT, like AP and AT is the same line basically, like, because like these lines AP, BQ, and C are intersected at point T, so AT is the same line as AP. So basically these lines, like AT, BT, and CT, they intersect, like as I just showed, they intersect at the angle 60 degrees. Like the angles between all these lines is 60 degrees. This angle is 60 degrees. This angle is 60 degrees. This angle is 60 degrees. This and this. So since the angles between all these 3 lines, between any 2 of them, is 60 degrees, then the angles between the lines that are perpendicular to them is also 60 degrees. So from these 3 perpendiculars, and from the fact that from the angle 60 degrees, So the angle, like, let's write it here also, the angle like so the angle between the line AT and BT is 60 degrees. The angle between BT and CT is 60 degrees, and the angle between the line CT and AT is also 60 degrees. So now from this and from this, it follows that, so from this and from this, it follows that that the angles between the lines perpendicular to them, so XY, YZ, and ZX, is also 60 degrees. So the angles between the line XY and YZ is equal to 60 degrees. The angle between YZ and ZX is equal to 60 degrees, and the angle between ZX and XY is also 60 degrees, right? But like we can see it just by a rotation by 90 degrees. So if you rotate these lines CT, AT, and BT by 90 degrees, then they would be mapped to the lines parallel to XY, YZ, and ZX, and therefore and the angles between, like, under rotation, the rotation preserves the angles between lines. So yeah, so this is also 60 degrees, and this immediately proves the statement, because now the angles between XY, YZ, and ZX is 60 degrees. It means that the angles of these triangles are 60 degrees, and the triangle with angles 60 degrees, well, the triangle where all three angles are 60 degrees is equilateral. It's a well-known property. Okay, so the angles between these lines are 60 degrees. It means that these are the angles of the triangle, and this implies that this triangle is equilateral. So let's write this. So these angles are 60 degrees. From this it follows that the triangle XYZ is equilateral. And this concludes the proof. So yeah, so for the second theorem for the inward triangles, the proof is similar. So let's briefly repeat the argument. So we have this arbitrary triangle. We construct these triangles. So A, B, C, P, Q, R. So now we denote P prime, Q prime, and R prime, so that not to confuse it with the previous, with the outward triangles. And so we consider the centers of these triangles, which are the points. So X prime, Y prime, and Z prime. And we need to prove that this triangle X prime, Y prime, z prime is equilateral. So again, we consider the lines A P prime, B Q prime, and C R prime. So they all three intersect at a single point, which we will denote T prime. I guess we could denote T2, but like it doesn't matter, T prime, since we already denote all points with prime. So and we proved in one of the previous videos, like about the second Fermat-Torricelli point. This T prime, by the way, is exactly the second Fermat-Torricelli point of the triangle CBC. So we proved that the angles between these lines are 60 degrees. And we proved that the quadrilaterals B T prime, C P prime, basically the quadrilaterals consisting of these equilateral triangles plus the point T prime. So this quadrilateral then T prime C A Q prime and B T prime R prime A. So all three of them are cyclic. So we consider the circumcircles of these quadrilaterals, which are also the circumcircles of the equilateral triangles. So this and this. So we notice that x, y, and so x prime, y prime, and z prime are the centers. The centers of the circles. And so the line connecting the two centers, so for example x prime y prime is perpendicular to the common chord, to the line containing the common chord, which is CT prime. So if we extend here, so this is the right angle for the other two as well. So if we extend here, this would be the right angle, and here this is perpendicular to this. So let's write this. So this means that x prime y prime is perpendicular to CT prime, y prime z prime is perpendicular to BT prime, and z prime x prime is perpendicular to AT prime. No. Y prime z prime is okay, so this is perpendicular to AT prime, and this is perpendicular to BT prime. Yeah. So, and as already mentioned, the angles between the lines AT prime and BT prime is equal to the angle between BT prime and CT prime, and the angle between CT prime and AT prime, all of them are equal to 60 degrees. And so from these two properties we conclude that the angles between the perpendicular lines to these three, AT prime, BT prime, and CT prime, which is x prime, y prime, so the angles between x prime, y prime y prime z prime is equal to the angle between y prime z prime z prime x prime is equal to the angle between z prime x prime and x prime y prime is equal to 60 degrees, and this immediately means so basically these three angles are equal to 60 degrees, and this implies immediately that the triangle x prime y prime z prime is equilateral. This concludes the proof.